continuity is a special property of functions. It's a property we've secretly alluded to already, but now we'll discuss it properly. We say that a function f is continuous at c if when we evaluate the limit at c, we get the same value as the function itself. Effectively, this says that the function is well behaved at c. What f does at the point c agrees with its behavior near c. When a function is continuous at every point in its domain, we'll just say that it's continuous. Okay, so we already know of at least one class of continuous functions, namely the set of rational functions. Recall that these are functions that are of the form of polynomial over polynomial. And we saw that these are continuous so long as the denominator is non-zero at the limiting point. Now you may freely assume that the following functions are continuous on their specified domains as well. So any function of the form x to the power of a, where a is some positive number, is going to be continuous on 0 infinity. Flipping things around, the exponentials a to the x are continuous for every real number, so long as a is positive, and the logarithms with any positive base are continuous as long as x is in 0 infinity. Finally, the absolute value is also continuous everywhere. Okay, so you can assume these for free. So to ground ourselves, let's look at a function which is not continuous. So this function evidently does something weird at the point x equals 2. To check whether or not it's continuous, let's look at the limit as we approach 2. First, we can evaluate the limit and ignore what's actually happening at 2. And remember that this is because when we take limits, we only look at what happens near 2, not at 2. Now we're familiar with these sorts of limits, where we can factor the numerator and see that it shares a term in common with the denominator. Again, we can cancel out the x minus 2 terms precisely because x is not equal to 2 in the limit. Doing this gives us our limit of 4. However, the actual value of f at 2 is equal to 7, which does not agree with the limit. Hence, f is not continuous at x equals 2. Now, before doing any examples, let's see that we can immediately apply the limit laws to continuous functions. So if f and g are continuous at c, and alpha is a real number, then f plus g, fg, alpha f, and f over g are all continuous at c as well, with the usual caveat that in the last case we need g of c to be non-zero. To see why this is an application of the limit laws, let's look at the sum. We know that limits of f and g because we assumed that they were continuous. And in particular, they both exist. So when we take the limit of their sum, we can write this as the sum of their limits. Each of these is just the value of the function at the point c, and if we look at the first and final terms, this is exactly what it means for f plus g to be continuous at c. Now we can use this to quickly evaluate limits of functions. Here's a big nasty function, and we want its limit at 4. However, each part of this function is continuous. We've got a polynomial, we've got a square root, and we've got an exponential, right? All of which we know are continuous. So we just need to make sure that the denominator is not 0 at x equals 4, and of course it's not. So the whole function is continuous, and that means that we can thus evaluate the limit just by plugging x equals 4 into the function, and that gives out an answer of a half. Okay, so the dual problem to what we just did is to determine where a function fails to be continuous. Let's look at this function. Again, all of the parts of this function are continuous, right? So the only possible issue that we could have is when the denominator is equal to 0. So we can find the roots of x squared minus 9 pretty quickly, giving us x equals negative 3 and x equals plus 3. So we conclude that f is continuous everywhere except negative 3 and plus 3. Okay, the hardest example now, let's take a look at a function which has variables as part of its definition, and see if we can find all the values of, in this case, a, which make this function continuous. For any value of a, each of the pieces of f will be continuous, so we need only look at what happens when x is equal to 1. According to our definition, we want the limit of f of x to be the value f of 1, which we can work out as so. Actually, evaluating the limits gives us the following. From the right, we get the value a squared plus a plus 1, so that limit already agrees with f of 1, and from the left, we use the second half of the definition of f to get 3 plus 2a. Now these have to be equal to one another. So by equating them, we can solve for a as follows. And so this function is continuous precisely when a is either -1 or 2.